so what I'm going to attempt to do in over the course of 3 lectures is basically work through one example of algebraic invariance of a toy sector of low-dimensional topology. So the toy sector of low-dimensional topology is that of braids and braid cobordisms. So this is a toy piece of a world that many of you care about. And the invariance, the kind of invariance that we'll be considering are algebraic invariants. So invariance coming from homological algebra. And in this case, homological algebra means we'll be working with complexes of modules over a finite dimensional algebra. So this is actually, in some sense, the example that I want to go through in a bit of detail is, in some sense, the simplest example of an algebraic invariant of this section of topology. Okay, so that's where we're headed. This, what we'll do here is independent of, but parallel to what Eli will talk about. In particular, I'm not going to say a lot about this kind of world, maybe a little bit in the 3rd lecture. So this is all closely related to Khovanov homology and annular Khovanov homology, but in some senses more basic and an even more toy model than there. Okay, so hopefully caring about these things is enough motivation to learn this example. Despite the fact that it's a toy model, it's also extremely rich. So hopefully one of the things I want to convince you is that there's a very deep relationship between representation theory of these finite dimensional algebras and topology. But I thought maybe, so today's lecture, maybe the first half of it, I just want to say a little bit of nonsense in an attempt to motivate this story a little bit. So the basic thing we're going to do over the, concretely is I'm going to tell you about a particular category, and this category is going to have an action of a group on it. That group is going to be the braid group. So the Artin braid group is going to act on this category. So in some sense, the concrete goal of the first lecture is to explain what that means. And before I explain what it means, I want to try to convince you that you might care. And well, you might care for topological reasons. If you like representation theory, then you already care. That's fine. And but you also might like groups. And so I want to maybe talk about it from that perspective for a moment. So this will be these lectures will be on the board for the most part, but I want to show you a few slides first. Half of which were stolen from Jordy Williamson. So this may be historical. So group. So where did the term group come from? I think it's French from the word group. So it was coined by Galois. So that's in the 1800s. So this is a page from a letter Galois wrote to Chevalier in I think maybe 4 or 5 days before he was killed in a duel. So on this page, there's a tremendous amount of mathematics. And on the right, you can see the notion of a normal subgroup appears, a simple group, a solvable group, the main theorem of Galois theory in that last sentence. There was a lot of other interesting stuff in this letter. It's pretty cool. So that's 1830. So 60 years went by before any mathematicians started thinking about groups as they appear in linear algebra, in particular as linear actions of groups. So the first person to do that was Frobenius. So that's Frobenius, and that's in the late 1800s. So this is the first character table published. This is Frobenius. This is the character table of the symmetries of the tetrahedron. So that's 1896. So group theory had been around for 60 years, but and Frobenius did a lot of work early on that made it clear it was a fairly rich subject, but it wasn't obvious. Oh, by the way, yeah. So this is the monster. This is 2 pages of this is now much later. This is a bit of the character table of the monster, which I mean the whole character table takes up maybe 8 or 9 pages in the atlas. This is 2 of them. Maybe but initially, people interested in groups weren't convinced that representation theory had anything interesting to say. So this is an excerpt from Burnside theory of groups of finite order. this is around the time that Frobenius defined character, and Burnside certainly knew about Frobenius's work. Later on, it would turn out that Burnside himself was a kind of early giant in representation theory, which you might be surprised if you read this thing. So, in particular, he says, so in the first, he says, at a present state of knowledge, many results in the pure theory are arrived at most readily by dealing with properties of substitution groups. It'd be difficult to find a result that could be most directly obtained by consideration of groups of linear transformation. So he's basically saying, I don't see any application, so we're not going to talk about it. But 15 years later, he wrote a preface to the second edition and then says, in fact, it's now more true to say that for further advances, one must look largely to the representation theory of a group as a group of linear substitution. So to me, this is kind of to Burnside's great credit. And in the interim, he himself had done some significant work here. So this is 1911. Okay, so that's. I also think it's curious. This is. Look at the group. If you want, this is how Burnside wrote the definition of a group in that second one. So this is like 70 years of abstract groups. I tempted to use this text in undergraduate algebra. Okay, so in the philosophy here is that representation theory is useful. Why? Well, if you care about groups, you definitely care about group actions, and group actions are hard to study, but linear group actions, representations, are not necessarily hard to study. And in the last 100 years, mathematicians have developed a lot of tools to take actions they care about and linearize them, and get information that way. So, okay. So basic examples, really examples. Let's say you have a finite group. I mean, classifying actions of a finite group on a set is a hard problem, but looking at permutation representations is much easier and tells you a lot. In some sense, older example, the circle acting on itself. Well, instead, you can look at the circle acting on L2 functions. That's the theory of Fourier series. There are certainly other deeper examples of this sort of thing. So this is what I mean by linearize. Instead of thinking of S1 acting on itself, think about it acting on an L2 function. Okay. So categories, of course, are perfectly reasonable objects to study and study their symmetry. And categories, well, certain types of categories, linear categories, are, from many points of view, just as good as vector spaces in terms of as objects of linear algebra. And groups act on linear categories, and one should think of groups acting on linear categories much the same way as one thinks about groups acting on vector spaces. The question, if you're interested in groups, is should you care? So, I mean, it's a little subtle to say what should count as a linear action of a group on a category, but you should think your category should have the structure that allows you to categorify linear algebra. So maybe you should have be able to take direct sums. Maybe the Hom spaces in your categories should themselves be vector spaces. Maybe you should have exact sequences and be able to talk about sub-objects and quotient objects, etc. So, examples. So sometimes the point is that sometimes if you have a group action, the most natural linearization of it is not a vector space. Sometimes the most natural linearization is a category. So, for example, if X is a space, then the category of coherent sheaves on X, or the derived category of coherent sheaves, those are perfectly good linearizations of X. And you should think of them much the same way as one might think about replacing a space by functions on the space. Maybe slightly more subtle, so if you use a finite group, then if you're working over a field of characteristic 0 and you want a characteristic 0 linearization of your group, well, the character table gives you one. That's a slightly obscure way of saying that the group algebra of G is semi-simple. So the group algebra is, but if you're interested in representations of G over fields of finite characteristic, where the group algebra is not semi-simple, it's not a product of matrix algebras, then the character table is not a very good linearization of the group. Instead, maybe the category of modules over the group algebra, which is no longer semi-simple, or the derived category of that, those are better candidates for notion of a linearization of a group. Okay. So I'm not going to say a lot about that, but it will maybe come up a little later. Okay, so actions of categories on groups are not new in mathematics. They've been around for a while. But for the most part, the interest in these actions is that there's some category which you're interested in first, and you study the group action because you want to understand this category, so you want to understand its symmetries. So usually, at least in the last 20 or 30 years, when one studies the action of a group on a category, it's not because you care about the group, it's because you care about the category. And that's a little unfortunate because it means that people who really care about groups are not necessarily interested in actions of groups on linear categories. But I would like to argue that that situation is changing, and it's sort of the responsibility of people who are studying groups acting on categories to try to prove some new theorems about groups. And, well, one of the tasks there is to figure out which groups you should try to prove new theorems about. And so to do that, you should try to find examples of groups that are hard to study using classical representation theory, because they don't act very naturally on vector spaces, or when they do act on vector spaces, you lose a lot of information. And many of the groups that low-dimensional topologists and geometers care about are exactly groups of this form. Mapping class groups of surfaces, fundamental groups of three manifolds, braid groups. These groups are notoriously difficult to study using finite dimensional linear algebra, using representations on finite dimensional vector spaces. And, but these groups also act on linear categories, and so one of the things that should start to happen is people should try to study the groups by using some of these categorical actions. And this example that we'll talk about today, in the 3 lectures, the whole point will be for me to try to tell you a lot, that you can learn a lot about the braid group by studying its first non-trivial linear categorical action. That's the whole point. Okay, so now it's done with the slides, so let me move to the board. So any questions before we start doing some real mathematics? Okay. Okay, so let me tell you what I mean by an action of a group on a category, because there are several things that one can mean, and they're all important. So let's let G be a group, and C a category. So an action of G on C is what? Well, what kind of data do I have to give you? So to each element in the group, I have an invertible endofunctor of C. So a functor from C to itself, which is invertible. So in particular, the unit in the group will go to something isomorphic. Will go to the identity functor. And so what condition has to hold? Well, the condition which has to hold is that if I look at the composition of the endofunctor for G and the endofunctor for H, that should be isomorphic to the endofunctor for GH. Okay. So this is a definition. So this definition should be called and sometimes called a weak action of G on C. So why is it a weak action? It's a weak action because I've demanded this condition, but I have not specified the isomorphism. So at the other end, sort of at the other end of the spectrum, there is the notion of a strict action or a genuine action. So a strict action specifies isomorphisms and requires them to satisfy an associativity constraint, which one way to write it maybe is that you could have FGHK, which on the one is isomorphic to FGFHK. It's also isomorphic to, isomorphic by an isomorphism we've given to FGFHK, and that's of course FGFHK in two ways. And so you require this diagram, you require these isomorphisms to make a commutative diagram like this for all GH and G. So that would be a strict action or a genuine action. So the action that we're going to, the Braid group action we're going to talk about, I'm only going to describe it as a weak action, but it can be made strict. To make it strict, I have to give you more information than I've given.
So you only need to do this for these triple compositions? Or?
That's right, yeah. If you have it for all of these, then the larger possible associative diagrams you draw will all commute. So those are sort of two ends of the spectrum.
So you're saying there's like a comparing step that gets you from the weak to the strict?
I'm not saying that if somebody hands you a weak action, you can make it strict. That you may or may not be able to make it strict. I'm simply saying that one might care about a strict action, in which case you're required to produce other information. So it's a very interesting question in general, what you need, what kind of information you need in order to, if you're handed a weak action, to make it strict. So in general, I don't think much is known about this. But in the case of the Braid, that's a kind of reasonable point. In the case of the Braid group, so Deligne gave a criterion for what you need to check, a simple criterion for what you need to check in order to say that a weak action of the Braid group is strict. His condition involves just saying something for all positive braids. And then also Elias Williamson also have a condition different than Deligne's that one can use to show that a weak action of the Braid group is strict. These are genuinely different conditions. Deligne requires you to say something about a lot of braids, but you don't have to say you don't have to check very much. Elias Williamson don't ask you to say much to provide information about very many braids, but you have to check quite a lot of information about those few braids. Okay. Okay, so
yes, you square like GH somewhere. You could say this.
Oh, thank you. Thank you. Great. Okay, so that's what we're looking for. So what kind of categories? So I think one of the unfortunate things, if you don't think about groups acting on categories very much, is that I'm claiming that this is somehow maybe a very simple example, but the category that we're acting on is a triangulated category. And if you don't think about triangulated categories, that's a unfortunately intimidating word. So I want to say a little bit about why most of the literature on group actions of this sort ends up acting on triangulated categories as opposed to abelian categories or categories which may be more familiar. So, okay, so in algebra, the kind of easiest kind of category to think about is the category of modules over a ring. So categories of modules over a ring are abelian categories. You have exact sequences, sub-objects, etc. So let's let A be an abelian category. So in particular, you can talk about exact sequences, sub-objects, etc. And you should think here A is modules over a ring. So what kinds of group actions can you have on such categories? Well, one way to think about what kind of group actions you can have in a category is to look at what a category like this is, you can look at what kind of group actions you get at the decategorified level, so at the growth and group. So let's let K0a denote the growth and group. So for me, the growth and group is just going to be a vector space over the complex numbers. So by definition, the growth and group is going to be a vector space. It's going to be a vector space spanned by, I'm just going to take a vector for every object of my category. This is some sort of huge complex vector space. But then I'm going to mod out by the relation that x plus y equals z whenever there's an exact sequence x, z, y, 0, and a. So every time I have an exact sequence, I impose this relation on the vectors. So if f is an exact functor, exact just means it takes exact sequences to takes short exact sequences to short exact sequences, then f induces a linear map on the growth and group. C linear map. So, but now, so you can ask, one thing you can ask is you can ask what kind of linear maps can you get if f is invertible? So if f comes from a group action so that f is invertible, what kind of linear maps can you get here? But okay, so let's say S1, Sk be the simple objects of A. So what is a simple object in the abelian category? It's an object which has no proper sub-objects other than 0. So let's say you have the simple object. So if f from A to A is invertible, in other words, for example, if it's coming from an action of a group, and then if Si is simple, what can you say about its image under this functor? Well, it's also simple, because any sub-object here you could pull back to give you a sub-object by applying the inverse functor. Okay? So this is also simple. So in other words, if you look at the basis, if you write down the matrix for this linear transformation in the basis of simple objects, it's just a permutation matrix. So the matrix of F, written in the basis of the classes of simple objects, is boring. So if you have some interesting linear transformation and you want, on the growth and group that you want to lift, then the category you're acting on can't just be an abelian category. It's got to be more interesting than that. So this is so it's like finding groups acting on abelian categories is kind of like the question of find an endomorphism of a vector space which fixes a particular basis set-wise. Not so interesting. So,
So which abelian categories are the collection of simple objects actually like a set or finite set?
Well, I mean, if you're looking at the category of finitely generated representations of a ring. Yeah, yeah. And in particular, I mean, the point is that these classes in the growth and group, I mean, even if this is not a set, then in the growth and group, their classes is a perfectly good set. So, I mean, here, if you want, you can just take R to be a ring or maybe a finite dimensional algebra or something, and there's no issues like that. For us, the algebra will just be working with finite dimensional algebra. Okay, so that was a kind of long-winded way to explain to you why we're going to end up dealing with triangulated categories a little bit. Okay. So I think that's the end of the general nonsense. So any questions about this? Okay, so where are we headed? I want to tell you about a particular action of the Braid group on a particular category. So the goal for the rest of the talk is going to be to explain to you what category the Braid group is going to act on. It's going to be a category of representations of an algebra, so I have to tell you what algebra. Okay. Okay, so let's talk about path algebras for a moment. Okay, so let gamma be a quiver. So quiver means an oriented finite graph, vertices and oriented edges. So actually, in our lecture series, there's only one quiver that we're going to be interested in, which I'll get to in a moment. But so this is an example, and I'm going to name the vertices. And maybe we should also name the edges. So a path in gamma is exactly what it sounds like. It's a path which starts at some vertex, moves along oriented edges consistent with the orientation, and ends at some other vertex. So, for example, you could start at vertex 1, then you could go by alpha to vertex 2, and then by beta to vertex 3, and maybe you end up at 3. This is a perfectly good path. So in this particular quiver, actually, since there's at most one edge between different vertices, I could really just tell you a sequence of vertices. So the path algebra of the quiver gamma is the algebra, say over the complex numbers, with basis given by all paths. So every path in the quiver is a vector in this vector space, and the multiplication is just concatenation of paths. Concatenation of paths. Now to concatenate paths, if I've got a path which ends somewhere and another path which starts somewhere, to concatenate them, the ending place of the first guy has to be the starting place of the next guy. So that's when I concatenate them. If those don't match, I just declare the product to be 0. So that makes this into an algebra. So here's maybe an example. Let's say just a simple example to start with. So if this is my quiver, then the path algebra. Let me not call it C gamma. Let me call it path gamma. So path gamma is a vector space. In this case, it's going to be a 6-dimensional vector space. So what are the paths? Well, you have the length 0 paths at each of the vertices. So I'm just drawing those like that. So this 1 denotes the length 0 path starting and ending at vertex 1. And similarly. What else do you have? You have the path from 1 to 2 going through alpha. So 1 to 2. This is alpha. You've got the path from 2 to 3. This is beta. And you've got the path from 1 to 3 through 2. So these are the only paths. And note that, for instance, if you do beta times alpha, that's 0. If you do beta first and then alpha, beta ends at 3, alpha starts at 1, so that product is 0. Also, for example, note that 1 times 1 is 1. The product of the length 0 paths is, so the length 0 paths are idempotents. So something you can check if you want to play around for a moment is check that the sum of these 3 is the unit. So this algebra has a unit. This is the unit in this example. Okay. Okay, so now zigzag algebras. So gamma is our quiver, in this case just the same one, but this definition makes sense for arbitrary graphs. So here's our quiver. So I'm going to let gamma bar be the doubled quiver. So the doubled quiver, I double every edge, and I put the doubled guy in the other orientation. So now, if two vertices did not have an edge before, they still don't have an edge between them. And if they had an edge before, now they have two edges, one in each orientation. Okay. The algebra we're going to be interested in, call it A sub n, this is called the zigzag algebra, is a quotient of the path algebra of the doubled quiver. So okay. So the path algebra of the doubled quiver modulo some relations. I'll tell you the relations in a moment. Note in this example, there's a big difference between the path algebra of the doubled quiver and the path algebra of the original quiver. The path algebra of this original quiver is a finite dimensional algebra. The path algebra of the doubled quiver is infinite dimensional. There's lots of loops here which you can just keep doing. Okay, so what are the relations? I'm going to impose enough relations to chop this infinite dimensional algebra down to a finite dimensional algebra. So where the relations are as follows. So the first is that that any length 2 path which starts and ends at distinct vertices is 0. So in particular, if you're at vertex I and you go to vertex I plus 1 and then to vertex I plus 2, we kill that path. And similarly for the length 2 path going the other direction. So the length 2 paths which start and end at distinct vertices are all killed. Okay, so what length 2 paths do we have left in the path algebra of the doubled quiver? Well, we have the length 2 paths which start and end at the same vertex. So, for example, we have at vertex I, we have a length 2 path which goes through vertex I plus 1 and then back. And we also have the length 2 path which starts at vertex I and goes through vertex I minus 1 and back. So the other relation we impose in the algebra is that these two guys are the same. Okay? So, right. So maybe slightly annoying point here. This is the definition as long as we have enough vertices, as long as n is greater than or equal to 3. So if you think about it, if n is 1 or 2, so we only have 1 or 2 vertices here, then I haven't told you anything here because both of these relations involve three distinct vertices. So by convention, A1 is just the algebra Cx mod x squared, and A2 is the path algebra of this guy, and you just kill all length 3 paths. Anyway, don't worry about that too much. Every statement I make about the algebras AN will hold for A1 and A2 with these definitions. Okay, so this algebra, I mean, it's not particularly interesting or enlightening to see an algebra defined this way. It's certainly, unless you've seen these things before, probably not at all clear why it has anything to do with the Braid group or low-dimensional topology. But this algebra shows up everywhere. It's ubiquitous, certainly in representation theory, and also in algebraic geometry and in symplectic geometry. So in the third lecture, hopefully, I'll say a little bit more about that. Okay. So this is the zigzag algebra. And these definitions make sense for arbitrary graphs, but we're only going to talk about it for this graph. One hint, One hint that it might be related to the Braid group is that the graph we started with is an orientation of the Dinkin diagram of type A. And the Braid group, the generalized Braid group associated to type A representation theory is the ordinary Braid group. So if you replace gamma by some other Dinkin diagram, much of this story will go through, except for instead of the Braid group, you'll have the Braid group associated to that Lie type. Okay. Okay, so that's the definition of path algebra and the zigzag algebra. So let's think a little bit about representations of the zigzag algebra. So there are some particularly important representations. So what are some representations of the zigzag algebra? So let's let Pi, p sub I on the right, be the vector space. As a vector space, it's spanned by all paths, modulo the zigzag relations, which end at I. So the algebra itself was a quotient of a path algebra by some relation. So in that path algebra, you got a bunch of paths. Look at all the paths which end at vertex I. So paths which end at vertex I, this is a vector space, but it's not just a vector space. It's a left module over the zigzag algebra. So Pi is actually it's an indecomposable projective left and on. And similarly, there's, let's say P, put the I on the other side. This would be the span of paths which start at I. This is a right module. Okay. So those guys are going to be important players in the definition. Where we're headed here is defining the categorical Braid group action. And these guys will be important players. So any questions about the definition of the algebra before? Okay. All right, so so here's an exercise. A couple basic exercises about the relations in the algebra and these things. So one is compute the dimension as a C vector space of AN. So find a basis of it. If you think about the relations, the point is the basis will consist of, you just have to count how many length 0 paths do you have, how many length 1 paths do you have, how many length 2 paths do you have, how many length 3 paths, etc. So the point of the exercise is to realize and prove for yourself that there are no length 3 paths. So length 3 and greater, there are no more paths. So the algebra has spanned, a basis is given by the length 0, length 1, and length 2 paths. So just count them. Yes?
These are all mod those same relations.
Yes, yeah. All the same relations. Okay, so let's, and here's one more exercise. This we won't really use. It's just a way to familiarize yourself with the algebra a little bit. So let's compute, or the exercise is to compute this vector space. So here, Pj, this is a left A module. Pi, this is a right A module. So you can tensor them over A. So this is just a vector space. So what vector space is this? Well, it depends on I and j. So when I and j are far apart, this is just 0. So when I and j are neighbors, this is a one-dimensional vector space, and it has a canonical basis given by the unique path from I to j. And when I equals j, this vector space is two-dimensional. It's I'm just writing the basis vector. It's got one basis vector. I'll explain this in a moment. let's see, xi. So I'll explain this in a second. So, so the point of this exercise is to compute that this tensor product is 0, a one-dimensional vector space, or a two-dimensional vector space, depending on what I and j are. And the hint, which isn't really a hint, it's just what you have to realize to see this immediately, is what is this vector space? This vector space is the span of all paths from I to j. Modulo the zigzag relations. So if I and j are far apart, there are no paths from I to j because the relations killed them all, etc. So, so here, what is this? So I should have introduced this notation before. So one of the zigzag relations was this one. It said in the algebra there's a unique length 2 path from I to itself. There's a path going this way and there's a path going this way, but we've declared them to be the same. So that path that length 2 path I'm calling x sub I. It's in the algebra it's the unique length 2 path from I to itself. So paths from I to I, there are 2 paths from I to I. There's the length 0 path and the length 2 path. Okay? Okay, so that's these are two exercises to do. So one more important player. Let's let's see. Maybe one more remark. So note, this is a non-negatively graded algebra. Actually, it has a lot of interesting gradings, but there's one obvious grading. So what is the obvious non-trivial grading on the zigzag algebra? Well, a path algebra is always graded by path length because the multiplication is concatenation of paths, which adds length. So the path algebra of any quiver is always graded with the grading given by path length. And the relations that I just erased are homogeneous for path length. So the grading by path length on the path algebra descends to a grading on the zigzag algebra. So this is a graded algebra graded by path length. So it's convenient, and so these modules, they're all graded modules. So we can keep track of the grading if we want. And so one more definition. Okay. So here, I took the tensor product of a right module with a left module over the algebra. Here I'm taking the tensor product of a left module with a right module. So what kind of object is this? This is a bimodule. This tensor product has a left action of A on this left module and a right action of A here. So this is, and for convenience, I'm going to shift the grading. This naturally has a grading given by path length. I'm just going to shift it. That's just a convention. So this is an AN bimodule. Okay. All right. So we'll come back to that in a moment. So let's have a quick detour to the Temperley-Lieb algebra. Okay. So the Temperley-Lieb algebra is an algebra over ring of functions in a formal parameter Q. So this is the field that our algebra is going to be defined over. And the Temperley-Lieb algebra is generated by, so the generators there are n of them. And the defining relations in these generators satisfy are the following. So ui squared is q plus q inverse ui. Ui plus or minus 1 ui is ui. and ui, uj, ui and uj commute when they're far apart. Okay, so this is the Temperley-Lieb algebra. And the Temperley-Lieb algebra has a nice planar graphical description. So for UI, what you draw a picture which is straight lines for everything except I and I plus 1. And then you put a cap there. So this is I plus 1. So this is what we draw for the generator u sub I. Multiplication in the algebra is concatenation of diagrams, but up to isotopy. So these are the generators. Multiplication is concatenation of diagrams, which I'll draw in a second. And but anytime you have a closed circle, you can erase it at the cost of replacing it by the value q plus q inverse. Closed circle has the value q plus q inverse, quantum 2. And so then these defining relations all acquire planar diagrammatic interpretation. So for example, ui plus 1 ui, let's draw that. So ui, and then shove ui plus 1 up on top of it. And then, oops, and then ui again.
Are you reading bottom to top or top to bottom?
I'm reading bottom to top. But in this case, you could read top to bottom if you want. Yeah, I always read bottom to top and right to left. OK, so but this picture is isotopic rel boundary to UI. So this is the graphical, and similarly for the other ones. This one is just you can isotope the heights of these things when they don't interact at all. So this, it's maybe also worth noting, this Temperley-Lieb algebra, this is also the point of contact that the not homology program has with our subfactory partners. I don't know if there are any other points of interaction, but the Temperley-Lieb algebra is a central object in C-star algebras and in the study of semi-simple tensor categories. OK. So, so that's just the definition of the Temperley-Lieb algebra. So now here's another exercise, let's go back to let's think again about these bimodules over the zigzag algebra, and let's do another computation. Before I do the computation, I want to do one last point. So now, I mean, introducing the Temperley-Lieb algebra is very close to talking about the Braid group. So in particular, so I'm not going to say too much about the Braid group in this talk. I'll say a lot more about it at the beginning of the next talk. But as a bit of foreshadowing, there's a homomorphism. I mean, there's a morphism from the Braid group to the Temperley-Lieb algebra that takes the standard generator of the Braid group to 1 minus QUI.
Tony, I think, Ben, you want to n minus 1 as opposed to n.
Oh, thank you. OK. So this is OK. So this is a morphism of monoids, if you like, because the right side is not a group. OK. So so now let's do a computation with these bimodules over the zigzag algebra. So here's an exercise which we'll do some of. So let's consider, so the tensor product of UI with itself, tensor product over what? Well, you always tensor over whatever's acting. So this is an AA bimodule, this is an AA bimodule, so here I'm tensoring over A. So this is an AA bimodule, and it's isomorphic to a direct sum of two AA bimodules with grading shifts. Don't worry so much about the grading shift right now. So now what about UI tensor UI plus minus 1 UI? So this is isomorphic to UI, and UI tensor UJ is 0 when I and j are far apart. Okay, so let's do part of that. But let's look at the first one. So I'm going to forget the grading shift for a second, but let's look at UI tensor over AN with UI. Well, what is that? Well, UI is UI itself was a tensor product of a left module and a right module. So let's just reorganize that a little bit. Tensor over C with okay. So yes.
What would you send I minus 1 to? Would you send it there?
Oh, so here. So does that make sense?
Sorry.
Yes.
So for now, we don't care what complex number Q is. Right.
Q is an indeterminate.
Oh, okay. So it's not
Wait, yeah, I'm taking the temporally Lie algebra to be a vector space over functions in Q.
Okay.
I mean, you could indeed take, I mean, it makes perfect sense to take Q to have a numerical value, but I'm not doing that. Question? Okay, so this computation, so we have a tensor product of two bimodules, and that's this left module tensor with this vector space, tensor with this right module. So what vector space is this? So we wrote down the answer. So what's the dimension of this vector space in the middle? It's two-dimensional. It's paths from I to I in the zigzag algebra. And there's the length 0 path and the length 2 path. So this is a direct sum of this guy plus itself. And if you keep track of the gradings, one of them will be shifted up and one will be shifted down. And what is this? This was, sorry. This is, I'll put the gradings in the end. This was a shift of this guy and a shift of this guy, and this was UI plus UI. So two copies of UI. So this is a bimodule realization of the temporally Lie algebra. It's a slightly degenerate one because of this. So in particular, this particular bimodule realization of the temporally Lie algebra will not extend to a particularly interesting invariant of tangles. But it does extend to a pretty interesting invariant of braids. I mean, it does give you a tangle invariant. But the tangle invariant doesn't have a lot of interesting information because of this. You have to do something a little bit richer if you want to get an interesting tangle invariant. One way to get a more interesting tangle invariant is instead of working with the zigzag algebra to work with the Khovanov arc algebras or something like this. So what we have, and we're almost out of time, but so where have we gotten to? So there's this finite dimensional zigzag algebra and basic bimodules over the zigzag algebra categorify the temporally Lie algebra. So now we're not going to study the temporally Lieb algebra. We want to study the Braid group. So so we need to somehow think about this. So we want to lift this this relation to something involving bimodules. So we want to kind of take the difference between two bimodules. So now one needs either you've seen these things before or you need a little bit of insight. The point is that what this is going to lift to is not a bimodule, but rather a complex of bimodules. So in order to bring the Braid group into the game, we're not going to deal with representations of the zigzag algebra, but rather complexes of representations of the zigzag algebra. This is not, the Braid group is not going to act by a bimodule, but rather by a complex of bimodules. So the goal at the beginning of next time is going to be to, so we've already lifted these UIs to bimodules, so now we're going to lift these expressions to complexes of bimodules and explain how that gives us a categorical action of the Braid group. And then, so after defining that, a lecture and a half or something will be devoted to me telling you as much as I can about what structure that in the Braid group can be seen in this 2 representation. So various positive monoids, various metrics on the group, various sorts of things like that. So that's where we're headed. So in the last minute, I think I just want to make one more motivational point, which I meant to say earlier, but yes.
One question. You say categorified the temporary Lieb algebra or quotient of temporary Lieb algebra?
This quotient of the temporally Lieb algebra, which you might, which I think is natural to refer to as the true temporally Lieb algebra. This is maybe one thing to say about this is this guy's a quotient of the Hecke algebra. What quotient of the Hecke algebra is it? If you look at the Hecke algebra in its Kazhdan-Lustig basis, and you kill the long element of every the Kazhdan-Lustig basis element, which is long in any rank 2 parabolic subalgebra, then this is what you get. And that definition extends to other Hecke algebras. So if you have a Hecke algebra of some other type, and you want to say what's the temporally Lieb algebra of type E8? The temporally Lieb algebra of type E8, this is the definition of it. If you remove this, then I don't know what the temporally Lieb algebra of type E8 is exactly. Sorry, maybe that wasn't very good. Right, so one sort of final comment. So what I'm trying to convince you that if you're interested in groups, then maybe, like the Braid group or some other group, then groups acting on groups acting on abelian categories are maybe not so interesting, but groups acting on triangulated categories are very interesting. And there's another good reason, which I'm not going to talk about in these lectures, but which is, I think, just in terms of being informed, is very important. So I want to think of this as, this is maybe what you could call a 2 representation of G. And it carries a lot more information than a representation of G on a vector space could possibly carry. And one concrete way to see that is that from this, which you should think of as part of linear algebra, you can produce interesting topological actions of G on actual spaces. So in particular, if you have something like this, there's a lot of ways to take a triangulated category and produce a complex manifold or some other space of interest. So the best known and perhaps best studied is one can consider the moduli space of Bridgeland stability conditions on this. So if you have any triangulated category, then there's a notion of a stability condition on a triangulated category, and there's a moduli space of such things called the Bridgeland moduli space. This is a complex manifold. And if you have a group which acts on this triangulated category, then for free, this group acts on this manifold. And for the groups that we're interested in here, Braid groups, etc., many of the spaces that one might be interested in having this group act on arise as moduli spaces of stability conditions on categories. So for instance, the Braid group is a k pi 1, and the Braid group, one incarnation of it is pi 1 of a complement of hyperplanes. And the universal cover of that space, this contractible space, actually arises in this way from the two representation we're going to study. So, so if you're interested in the Braid group from the point of view of K-pi1 questions or something like that, in fact, this two representation, this first non-trivial one, is the input for understanding it from this point of view. Okay, but I'm not going to tell you about stability conditions in the next couple talks, but it's at least an important thing to have heard about. Okay, I'll stop there.
Sorry, I have another naive question.
Yeah.
So it seems to me that you just described the decategorification process of taking a group action on a category and getting a group action on a manifold. Is there sort of a category, like a reverse categorification of taking, a group action on a space and then getting a canonical group action on a category, whereas so that
I wouldn't describe this as a decategorification.
Okay. But I'm wondering if in the same way that
So I mean, I'm not sure if this is what you're getting at, but one could pose a meta problem, which is suppose you hand me an action of a group on a space. Can I find a linear two representation of it so that the space arises as the moduli space of stability conditions or something like that? I mean, that's I have no idea what to say about that problem in general, but there are a ton of conjectures about what kind of spaces are supposed to arise as stability. So in certain cases, there are good candidates.
But more generally, is there in the same way that we take numbers and then we consider changes,
Sure.
these are the characteristics, or in that sense we categorify. Is there a notion of categorifying group actions on sets to group actions? Does that?
Well, in this framework, we're categorifying linear actions of groups on vector spaces by linear actions of linear categories.
And then is there a formal process that brings it down?
Oh, from a set? Well, you can, yeah, if you have any category, then you can consider the isomorphism classes of objects. So you can just forget all the structure of morphisms by just looking at objects up to isomorphism. That's a set. If you have a group which acts on your category by autoequivalences, then that's a set on which the group will act. But understanding that set involves understanding objects in your category up to isomorphism, which for a general category may or may not be doable.